Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here you have information about online seminars and study manuals for exams PFM, IFM, and LTAM that I offer. I direct the Actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help ISU actuary. Here's a problem for today for exam LTAM, long-term actuarial models. For a multiple state model, you were given that we have three states: state 0 healthy, state 1 disabled, state 2 dead, and you can go from state 0 being healthy to state 1 or state 2. From state 1 being disabled, you can go only to state 2 being dead, and state 2 being dead is absorbing, so once you get there you don't go anywhere anymore. The following forces of transition are given. mu01 is 0.02, mu02 is 0.03, mu12 is 0.05. Calculate the conditional probability that a healthy life on January 1st, 2004 is still healthy on January 1st, 2014, given that this person is not dead on January 1st, 2014. And here's the solution. Let us write H for the event that life considered in this problem is healthy on January 1st, 2014, and let E be the event that the same life is disabled, and D be the event that the life is dead. The probability that we are looking for is the probability of H given that D complement happened, so the person is not dead, which is the probability that H happened given that either H or E happened, and of course H and E are mutually exclusive. So this is probability of H intersection H union E divided by probability of H union E, and of course the intersection of H with H union E is just H, and H union E are mutually exclusive, so the probability of the union is the probability of the sum. So this becomes probability of H divided by probability of H plus probability of E. Now, what is probability of H? That's the probability that the person is healthy on January 1st, 2014, and the person is known to be healthy on January 1st, 2004. So this is the probability that this healthy person in state 0 is still in state 0 after 10 years. And you might wonder, well, do we worry about the fact that the person may leave state 0 and come back? And the answer is, you can't come back once you leave state 0. That's the way this problem is set up. So you don't have to worry about it because the two probabilities are the same. So this 10p00 is the same as 10p00 with a bar above 00. And anytime you have the calculation of p00 with a bar above it, that's just e to the minus integral over 10 years in this case, from 0 to 10, of the sum of the forces that are taking this life out of state 0 over those 10 years. Because this is really like the probability of survival under constant force. You either have death or survival in some other state. What is the force of mortality? I'm sorry, I said it wrong. You either have being healthy or you're in some other state. And the force that's taking the person out of state of being healthy is either this force that takes the person to state of being disabled, or state of being the force that takes the person to state of being dead. But you can combine those other two states of being disabled and dead and think about them as death in traditional life contingencies. So this is the probability of surviving being alive, subject to a total force of mu 0, 0, I'm sorry, mu 0, 1 plus mu 0 plus mu 0, 2, being the force that takes you out of this state of being healthy. Okay, so all this deliberation that I was just doing is to say that this is equal to e to the minus integral from 0 to 10 of mu 0, 1 plus mu 0, 2, which is like the total force taking you out of state 0. And so this is just like the constant force survival. What is the property of survival over n years under constant force? E to the minus n mu. In this case, it's the same as the integral e to the minus integral from 0 to 10 of 0.05t. And that's e to the minus mu times n, where mu is the sum of the two forces, so 0.05 times 10, which is e to the minus 0.5. Also, what is the probability of E? Well, it's the probability that the person goes from state 0 at time 0 to state 1 at time 10. And you may wonder, well, can the person go to some other states? The answer is the person can't return to state of being healthy. That's not allowed in the model. And if the person went to the other available state of being dead, that person can't come back to the state of being disabled at time 10. So there is no complication here. This is very straightforward. It's the probability over 10 years that at some point during those 10 years, this healthy person becomes disabled and then stays disabled, doesn't go anywhere else. So this is equal to the integral from 0 to 10 of Tp00, which is the probability of survival in state 0 from time 0 to until time t, times mu 01 dt, which is the probability of transition from state 0 to state 1 in the time period t to t plus dt, times 10 minus Tp11, which is the probability of survival in state 1 from time t until time 10. And if you aggregate all those over all possible values of t, this is the all possible ways of going from state 0 at time 0 to state 1 at time 10. Therefore, this integral is the property we're looking for. And this becomes the integral from 0 to 10 of e to the minus e to the minus integral from 0 to t of mu 01 plus mu 02 du, where u is a new variable that we introduced for the purpose of evaluating this. This is this Tp00 probability. Constant force, so mu 01, the transition force from 0 to 1, so multiplied by that constant force, times dt, that's the probability of instantly going to state 1. And then we want to survive in state 1. And remember, in state 1, you don't have a force of going back to state 0, so this probability of survival in state 1 is just e to the minus integral from t to 10 of of mu to the 1 2 ds. So now we note that e to the minus integral from 0 to t of mu 01 plus mu 02 du, where u is this new variable we introduced for this purpose, is e to the minus integral from 0 to t of 0.05 du, is what we call the variable. It doesn't really matter because it's constant force, so it's just e to the minus 0.05 times the length of the interval that we have, which is t. So e to the minus 0.05t. And what is the e to the minus integral from t to 10 of mu 1 2 ds? Well, it's e to the minus integral from s to 10 of 0.05 ds. And I changed I said it wrong. E to the minus integral from t to 10 of 0.05 ds. ds is the running variable, my apologies. Okay, now, this is constant force, 0.05 here. So what we get here by taking this integral is e to the minus 0.05 times the length of the interval, which is 10 minus t. Okay, now we plug it all into the calculation of the probability of e, and we get integral from 0 to 10 of e to the minus 0.05 t times 0.02 times e to the minus 0.05 10 minus t dt. Okay, we multiply it out. 0.02 we put in front, and inside what we're left with is the integral from 0 to 10 of e to the minus 0.5 times dt. That's a constant, so when you take the integral, it will be the length of the interval from 0 to 10, which is 10 times e to the minus 0.5, and then multiplied by that 0.02. So this is 0.2 times e to the minus 0.5. And what we're looking for is the property of h given d complement, which, based on what we showed before, is going to be equal to e to the minus 0.5 over e to the minus 0.5 plus 0.2 e to the minus 0.5. Now look at that. So we don't even have to calculate that e to the minus 0.5. It cancels out, and this becomes 1 over 1.2, or 5 over 6. It's just approximately 0.8333, and that's answer E. Please remember, this is copyrighted material. The problem itself comes from the Society of Actuaries. The solution is mine. Good luck in your studies, and good luck on the test.